Oh hi! In this video I would like to explain to you how you can calculate gravitational waves that come from a source in the universe, some astrophysical source. Now of course in general this is a very difficult problem because, well, of many reasons. One of them is very mathematical. Just the fact that the Einstein field equations, these things that relate the energy to the amount of curvature in the universe, are a very nonlinear mathematical differential equations, makes it very difficult to calculate these things properly. But there's also a conceptual difficulty. One of them is that the sources from which the gravitational waves come can themselves be very difficult, but also the gravitational waves on their way to the Earth can encounter all kinds of difficult things. For instance, and most notably, the curvature of the space through which they have to travel on their way to Earth. Now, we're going to make some simplifying assumptions to make the mathematics much more traceable. And one of the simplifications that we're going to make is that the source itself is quite simple in the sense that it doesn't move too fast. And also that you can approximate it by saying, you know what, it's really just one point mass, maybe in some orbit around another point mass. One other simplification that we're going to make is that the space through which the gravitational waves have to travel on their way to Earth is Minkowskian. So that means that on the way to Earth, space itself is Minkowski flat and doesn't have a curvature of its own. And finally, an approximation we're going to make is that the source from which the gravitational waves comes is very far away from the place where it is actually measured. Now, as follows. The starting point of all of this is, of course, indeed, the Einstein field equations. And what these equations tell you is how the curvature of space and time, that's this part, in some very difficult expression of the metric tensor, is related to this thing here, which is the energy momentum tensor, and it's a measure of how much energy, to be very strict, energy density and how much momentum density there is at a particular position in space. So it's this thing that will tell you what the source is that sends out the gravitational waves. Now, this part again is a measure of the curvature of space-time, and immediately I'm going to make a simplification, and that is I'm going to assume that the metric tensor that constructs this difficult expression over here is itself nothing else but the Minkowski space-time plus a small perturbation. And by Minkowski, I mean exactly what I meant before, namely that the gravitational wave, which is going to be this thing, the perturbation on top of the Minkowski, that the perturbation travels on top of something that itself is not curved. Now, that alone gives an enormous amount of simplification, and for the following reason. This difficult construction of metric tensors over here consists of second derivatives of the metric tensor. Now, if the metric tensor itself, this thing over here, would consist of a curved spacetime on which there is a gravitational wave, then this curved spacetime itself would depend on the coordinates of the spacetime. This thing would depend on the four coordinates of time and space. But that means that the second derivatives that appear over here make this a very complicated expression. Unless, of course, this is Minkowski, and one feature of a Minkowski spacetime in Cartesian coordinates is that these elements of the background curvature of spacetime are all constants. And that means that the second derivatives of these things are going to be zero throughout. And that's good news, because that means if we're going to take this thing and plug it into this difficult expression, all these derivatives with respect to the space-time coordinates of the background space-time will vanish. And the only thing that remains is going to be some difficult expression, still difficult, of this thing, the gravitational wave that we're looking for. So all in all, if you plug this in, I can already give you the answer. It's going to look like this. And this, of course, is a complicated, well, it's straightforward, but it takes a while is what I mean. It's a tedious exercise to put this into here and to find what's going to come out. So I'm going to skip that step and just going to tell you what it is. You will find that the second derivative of your gravitational wave with a minus sign plus the second spatial derivative of that same thing, but now with a plus sign, this is what comes out. I have to be a little bit more careful, because at the moment that you plug this into here, you will find that you will get some extra baggage over here, some more derivatives of this gravitational wave. But here's where general relativity comes to the rescue. One feature of general relativity is that you should be able to write down your mathematical equations, your laws of nature, in such a way that you can always go into some other coordinate frame. It's called a gauge transformation if you want to be strict about it, but the idea should be very simple. General relativity means you're always free to go to any other coordinate frame and still have correct laws of physics. Now, if you think about it a little bit more carefully, going to some other coordinate frame just means that you're going to start moving with respect to your original coordinate frame in a very particular way. And it turns out, as a mathematical exercise, that you can move in such a way that your new coordinate frame makes all this extra baggage disappear without compromising this part. I have to be very clear. You are completely free to do this as a hallmark of general relativity. You're not obliged to do so. You're also free to keep this coordinate frame with all this extra baggage, but you will make your life mathematically more difficult. So we're going to go to that coordinate frame, and that coordinate frame, by definition, make sure that these are gone. And to indicate that we're now in this coordinate frame, the usual notation is that you put over bars on these gravitational waves. It just means the gravitational waves as calculated in this very particular coordinate frame. Now, for the people who want to look it up, this coordinate frame is called the traceless transverse coordinate frame, traceless transverse coordinate frame, and that's for technical reasons. Very quickly put, the TT coordinate frame has a very special property that H 0I, and by this I mean that if your alpha is going to be the 0th row in your gravitational wave, in this metric, and the beta is going to be one of the spatial ones, so x, y, and z, one of these three, but not time itself, that these are all 0. Again, you're free to do this without compromising any of your physics. This is what defines the one of the t's, the transverse. But there's also the traceless, and by this I mean that if you take all the diagonal components of your space-time metric, so that means if you take 0, 0 and you add it to plus 1, 1, plus 2, 2, plus 3, 3, then this itself is also 0. This is called the traceless, because in a matrix, and as you know, a metric tensor you can always write as a matrix. The trace of a matrix is the sum of its diagonal elements, and this is the sum of the diagonal elements. So traceless means a metric, or matrix if you will, of which the sum of the diagonal components are exactly 0. So that's this. So this is the TT gauge, and again, going through to this coordinate frame in which the TT gauge holds means that all this extra baggage is gone, and this is now what we have for the left-hand side of your Einstein field equation. Now the right-hand side is still the same thing. In fact, there might be an overall minus sign, but let's word, yeah, there is. But let's just write it down. If you plug this into here, you will find that this was a plus and this was a minus. So I'm compensating for that by adding an extra minus over here. So this has still stayed the same. So there you go. We have now made the approximation, not the gauge, that's not an approximation. There's no compromise on the physics whatsoever by going into the TT gauge. The approximation that we've made is we're saying we're going to take the gravitational wave on top of a Minkowski spacetime. So that's approximation 1. Then we end up over here, which in principle is something we can solve because it's just a differential equation. Your H alpha beta, your gravitational wave itself, is a function in principle of time, because at any moment in time the perturbation that moves through space might be different, and it's also a function of space, because at any spatial position the gravitational perturbation will be a little bit different. So it will generally look like this. So we have a mathematical exercise now, and that is, given that somebody has told you how the energy density and momentum density in the universe looks like, or at the source where a gravitational wave is produced, can you then calculate what this thing should be? Now, it's a difficult exercise, mathematically speaking, but fortunately it has already been solved. So I'm just going to give you the answer, and if you want to check that it's the answer, just plug it back into this differential equation and see that it fits. Now, as a little side step, I'm going to show you what the solution to this thing is without all this extra baggage of this tensor thing. So as a little side note here, I'm just going to give you the mathematical equation that looks exactly like this, which is this one. Second derivative with respect to time, but let's say of some random function phi, plus 2 derivatives with respect to space of the same function phi, and suppose that it equals something, a source called j. This j can be any random function of time and space, t and vector x. This is the exact same differential equation as this one. The only difference is that I want to get rid of the fact that these are tensors, so I'm just going to show you how it works with a scalar function phi, and this part I've written as j. This equation might look familiar to people who have studied electrodynamics, because this thing is a very famous equation that occurs over there. It's called Laplacian equation, and it has a well-known solution. Now, again, we're not going to worry too much about how people found the solution. We're going to take the opposite route, where what I'm going to do is going to give you what the solution is, and you can check for yourself by plugging it back into this thing that it actually works. Now, if you do want to know where the solution comes from, you can pick up any book on relativity, any book on electrodynamics, or you can just watch the YouTube videos on my lecture series Electrodynamics, where I actually derive where this thing comes from. But again, I'm just going to give you the conclusion now. This thing, this phi of this mathematical equation, depends on time and the vector position, and is given by the following. It's minus 1 over 4 pi. Why 1 over 4 pi? It has something to do with the delta function. Again, you can check my lectures on electrodynamics to see where this comes from. And then it's an integration. And note the prime here. I will go into detail in a moment what that means. Of the following. J t minus x prime, absolute value, and x prime, and then divide everything by x minus x prime, absolute value. Again, I mentioned that the prime matters. Again, this is just a solution. Plug this thing into here and you will see that it fits. Now, just to tell you what these things mean, let me make a little picture of this. Suppose that what you have here is some coordinate system. There it is. So this might be x, this might be y, this might be z, and any position in this coordinate system is vector x. Now suppose that you are standing over here. This is the observer. So this is you. I'm going to remove the names of these axes because it doesn't really matter for my argument. And suppose that there's something here. It could be, in electrodynamics, some source of electromagnetic field. In gravity, this could be a particular group of masses grouped together. Now, any point, let's stick to the electromagnetic situation for now, just for brevity's sake, for definitiveness. Any point of this collection of stuff will have an influence on you over here. Now, your position as measured from the origin here is called x, vector x. Any point in this distribution of stuff that has an influence on you, we're going to call x prime. Then this distance from this piece of stuff having an influence on you, this distance here is then x minus x prime. It's just the difference between where you are and where the thing is. So this vector with the dotted line is x minus x prime. Now that's exactly what it says here. What it says here, if you read mathematics carefully, it says that what you feel over here is given by what this amount of stuff is. This is the stuff j, this j, the amount of stuff, but you have to calculate it for any piece of that stuff. So at any position x primed, calculate how much its influence of this piece of stuff x primed is on you. So that's what it says here. What you do have to do is calculate the amount of stuff at position x prime and calculate how you would feel it over here. And this is this part. You have to divide by your mutual distance between you and this piece of stuff. And you don't have to do it just for this piece of stuff, you also have to do it for this piece of stuff next to it, and this piece of stuff, and this piece of stuff. All in all, what you have to do is integrate over all these little pieces of stuff. And that gives you the integral. So you can sort of see where this solution comes from. It's just literally the sum of all the pieces of stuff J, each of which has an influence over you, and have to add everything together. That's what it says. Now there's a small assumption in here, and that is that the influence of this stuff drops off with the distance, right? The distance between you and every piece of stuff, x minus x primed, that's divided over, so there you go. So that means that the further away you are from that piece of stuff, the less influence it has over you. This is true both for electrodynamics and for gravity. So that's all there is to it. One small extra thing, you might notice here that at the position where there used to be time in your amount of stuff, because this amount of stuff might be changing in time, where there used to be time in our solution, it's time minus the distance between you and the stuff. It's t minus this distance. There's a reason for that as well. Again, here's some physics. The conceptual reason for this is that it takes time, travel time, for the influence of this amount of stuff to get to you. How much time does it take? Well, this distance divided by how fast it travels, in our case that's the speed of light for gravity and for electrodynamics. Now the speed of light I've put to 0. So what it really says here, x minus x primed with a velocity in there somewhere, literally is the amount of time that it takes for this influence to get to you. So at the moment that you're measuring at time t, you're not seeing it as it was at time t, you're seeing it as it was at time t minus the time that it took for this thing to travel, which is this number over here with an extra c somewhere. So all of this really directly translate to this thing over here. Now, having gone through that, we can go back to our situation here, because again, our differential equation that we have for the gravitational wave is really of this form. The only thing I have to change is, instead of calling this thing phi, I just call it now my gravitational wave, h alpha beta. And instead of this calling this thing j, the amount of stuff, I call it the amount of energy momentum at the source. So what I'm going to do, I'm going to just borrow this general solution and write it down immediately for my h alpha beta. Because again, it's the same mathematics, just different symbols. And if you do that, you will find, by the way, this should have been a 16 all along. That had to do with the fact that there was a factor of 2 somewhere floating around. Don't worry too much about it. If you get everything back in here, you will get that it is 4 times, right, the 16 pi and the 1 over 4 pi and the minus signs all drop out, so you end up with only one overall factor of 4, and you will get d3x primed t alpha beta t minus x primed comma x primed divided by x minus x primed. And there you go. Here is your expression for the gravitational wave that you feel over here when there is some masses, some energy momentum moving around over here. This is the general expression. The only approximation that I've made up to this point was that I've assumed that the background curvature, so the space through which the influence, the gravitational wave travels on its way to you, that stuff was Minkowskian. And there you go, there's your expression. Now, at this point, life has become very easy. The only thing that somebody has to do is just tell you how things are moving about here, how the masses are moving about. In other words, he has to tell you what t alpha beta is. It's some random function of time and space, depending on how things move over here. It could be 2 stars orbiting each other. If somebody has told you what t alpha beta is, you can just plug it in here, do the integration, and you just find the general expression. Now, depending on how difficult the stuff that's moving about here is, the more difficult your integration might be, and the more difficult your final solution for your gravitational wave might be. So we're going to make some more approximations. I told you I'm going to make 3 approximations. One is already made. There's 2 more. One of them is we're going to assume that this thing is very far away from where you are measuring, and that's going to give us an easier expression for this. The second thing we're going to approximate in a second is we're going to assume that whatever is moving about here, that itself is not relativistic, as it doesn't move with the speed of light or close to the speed of light or so. And under these 2 extra approximations, these 2 assumptions, this expression will become much more simple, and I will show you in a second. Now, before I do so, let's look at this thing just a second more. One thing that you can see if you look at this is that it drops off. The further away you are from the source, the less of this stuff you will see. And of course, that is very true. You can easily understand why that is the case, because gravity indeed drops off, even in Newtonian gravity, so the further away you are, the less of it you see. But that means that this in general is a very small number, and that's good, because over here we made the approximation that this thing is small compared to the background metric. So I'm just saying that we have justified our approximation that we made in the beginning. Now something more, and that is that the nice thing about this expression is that it can teach you something about the sources of gravity in the universe. Now this is hopefully what we measure using our gravitational wave detectors. Typically what you do, as I just told you, is that somebody gives you a T alpha beta, how things move about in this particular source, and then you can calculate the gravitational wave, but you can also do the exercise the other way around. If your gravitational wave detector have measured this thing, you can calculate back what the source has looked like. And this is of course how we use gravitational waves as messengers in the universe. It just really tells you, if you measure something over here, what has happened over there. So that could be telling you something about the equation of state of neutron stars, how strongly neutron stars are holding on to each other. It could tell you something about the masses of the black holes that are moving about each other. It could even tell you something about maybe the Big Bang itself. If this stuff over here was itself the Big Bang or something close or just right after the Big Bang. So this is very important in astrophysics, because if we measure this, we can calculate that and we know what happened in the universe. So it's very nice. Now onwards, let's make some more approximations. I'm going to erase this. 2 more approximations I'm going to make, as I told you. One of them is we're going to assume they're going to be very far away, us over here, very far away from what happens over here. And just by looking at the picture, or just by having your mathematics set already, if you're very far away from the source, then that means that this here is much smaller than that thing. If you just go far enough away, this has become a very big number, this has become, in comparison, a very small number. In other words, the approximation of us being very far away means that this thing, that is somewhat ubiquitous in our expression here, is well approximated just by you, where you are. So there's an approximation. You can also understand it conceptually, yes? Because if you're going to be very far away, then this amount of stuff to you is going to look extremely small. So all these pieces of stuff that you're integrating over are going to be very close together, right? The further away something is, the smaller something looks to you. And in other words, that means that the x primes are going to be very small compared to your x. So it's all just different ways of coming to the same conclusion. If you're going to be far away, then this thing is well approximated by that thing. Note that there's no prime here. Now this thing, it's the amount of distance from here to there, we're going to call r. Your distance from the source. Okay, so that's one thing. If we're going to put that in here, then a lot of things become much more easy, because this then becomes 4 times d3x prime t alpha beta. T minus this thing has now become t minus r. Again, there's a c missing as per usual standard. The c would have been here. If you put it back, don't worry too much about it. We're working c is 1 unit. This thing x primed is still there though, because x primed is the fact that you're integrating over all these little pieces of stuff, and that is still the case. So that one still remains. And here you have to divide by x minus x primed, this distance. But if you're very far away, then this distance has very closely become this distance, which we call r. And notice that r does not depend on x primed anymore. Now, if r does not depend on x primed anymore, that means you can take it outside of the integral, because you integrate over an x primed, and since the x primed is not within r, this thing just drops out, goes here. This is not a 4 over 2, it's a 4 over r. But my handwriting doesn't allow this to be very clear. So let me be very clear about it. This is 4 over r. And what remains within the integral is this thing, t minus r. And there you go. So here's already a somewhat easier expression for our gravitational wave, because we don't have to worry too much about what happens inside of here, just to how far away you are. So a more easy expression. We can do a little bit better. We still have one assumption to go, namely the idea that whatever happens here doesn't move with relativistic speed. I'm going to leave that until the very end. Just some mathematical trick first. You see, this part you can rewrite, and that's in the following way. What you have to do is use the fact that within relativity, the conservation of energy and momentum is built in. It's of course a sacred principle throughout physics. The conservation of energy, you cannot create energy or get rid of energy, and also the conservation of momentum, you cannot get rid of energy. Momentum, you cannot make momentum. And in relativity, these things are connected. The amount of energy leaving here is related to how much momentum is flowing away. This I hope you can easily see for yourself just by conceptual understanding. If you find that there's some energy missing over here, then that means the energy must have flown through space away from you, and flying through space of energy is what we call momentum. So these things are related to each other. Here's my little side note again. Simply put, it means the change in energy at one position in space is the same as the amount of momentum flowing away through space. And flowing away through space means a spatial derivative. Spatial derivative of your momentum. This is the conservation of energy and momentum. Now, I told you before that this thing doesn't really tell you what the energy momentum is, it tells you what the energy density is, the amount of energy per cubic meter and the amount of momentum per cubic meter. And to be very clear about this thing itself is a tensor. You can write it as a matrix, has two indices. And general relativity tells us that the 0, 0 index, this part over here, is exactly the energy per unit, cubic unit, so that's the energy density. This is 0, 0. And these parts over here, which will be the T0I, the spatial ones in the 0th row, these are the momenta. And to be very clear, it's momentum density, but typically people still write it as a momentum. Just for stupid reasons, people have decided not to use a new symbol for this. Just from context, you must understand P here stands for the momentum density. So there you go. The 0th row at the spatial positions gives you the momentum density. Same thing here, because it's symmetric tensor, it also works over here. And this stuff over here we just call Tij, and it's related to the angular momentum, how much spinning there's going on. So really this energy momentum tensor combines all the stuff that could be happening within the source. It could be the amount of energy itself, that's this number, the amount of flowing of energy, that's these numbers, and the amount of rotation of energies, and that's all the remaining parts. So this is, in brief, how you can view the energy momentum tensor. Now, going back to our conservation of energy and momentum, it just says that the amount of change of energy density in time should be minus the amount of spatial change of the momentum density. So that's this thing. That's all very nice. Let's put it into terms of the energy momentum tensor. Rho, as we saw, this is the t00 part. So it's the time derivative of t00, and it should be equal to the spatial derivative of your momenta. And the momenta are written as t0I, where I is one of the spatial directions. Now this derivative is itself an I, it's spatial derivatives, t0I. So just conceptually speaking, this is just the conservation of energy and momentum. And this is the conservation of energy density, momentum density, and the part over here really just stands for the exact same conceptual understanding, but now put in energy momentum tensor components. So here it is. Now I'm doing all this because what I want to do is I want to take this thing and in a moment plug it into this thing. Now in order to do so, you can do some mathematics on this. Now to do that, again, is a mathematical exercise that I'm going to skip. I'm just going to tell you what the answer is. If you do some mathematical manipulation on this, what you have to do is take another derivative on both sides, a time derivative. So you get two time derivatives, you get a time derivative and a spatial derivative over here. Integrate it over all space if you first multiply by two spatial positions. Why would you do that? Because the two spatial positions allow you to do 2 times integration by parts, blah 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 blah, go through the motions, and what you will end up with is the following expression, namely that d3x, so that means if you integrate over all space, of t, the two spatial ones now, is equal to, this is correct, checking my other board where I had a little side note so I wouldn't forget any factors as I've done before. Again, there's nothing difficult here, it's just skipping the mathematical steps. 2 times time derivatives, yeah, there we go. Integration d3x t00, that's it, xi and xj. So, I just have to check because my little memory board is right over there. And I didn't know this expression quite by heart, but there you go. Again, no difficulty here. This is really just our conceptual understanding of what it is to have a conserved energy momentum. Done another derivative with respect to time, so you get 2 time derivatives. Then I multiplied both sides by xij. I did it for a reason, namely that the 2 expressions that you then get if you integrate them and do the mathematical trick of integration by parts, you will ultimately end up with this expression. Again, the reason that I do this is because what I have here now, excuse me, including the dx3, is exactly what I have here. So just by the laws of mathematics and the fact that you have a conservation of energy and momentum, you can write this thing as minus, notice that the minus 1/2 cancels the 4 here, so you get 2 over r. And now I have to be very careful that you don't confuse the 2 and the r, but there you go. And instead of writing an integration over all of these, I now say, well, you just really get an integration of 2 time derivatives of this integration, t00 xi xj. Again, from here to here, it's just a mathematical translation of our conceptual understanding of the conservation of energy and momentum. Now, the careful watcher might have noticed now that there's something strange going on, because I start with alpha and beta, and I end up here with i's and j's. Now, an expression in tensor analysis cannot be the same on both sides of the equation at the moment that they don't have the same indices. And that is true. In order to use this trick, where it specifically says ij, only the spatial components, I've restricted myself only to the spatial components of my gravitational wave. Now, is that bad? Not really. For one thing, you can show that the other ones are very easily made 0, that's one. But most importantly, if we're going to calculate what the effect is on a gravitational wave on our detectors, we're only interested in what the gravitational wave does to our spatial parts. We're not interested in what it does to time. Now, in principle, you could calculate or you could measure a gravitational wave by looking at how much time dilation is different here than over here. That would be the h00, how much time dilation there is. What the effect is of this extra piece of curvature on your experience of time. But it's much easier, just for practical reasons, to calculate how much spatial difference there is. This is what we do in actual real life. We have a gravitational wave detector, which is typically two of these arms, interferometer, and one of the arms gets a little bigger, the other one gets a little smaller, and that is what we measure. It's just, practically speaking, much more easy to calculate the difference in spatial direction than in temporal direction. So I've taken this expression and I specialize it to only the spatial part. And because it's not a spatial part, an I in j, this alpha beta has become ij. And via this mathematical trick, it has turned into 2 times a time derivative of now the t00. So we've really specialized now to this particular expression. Now we're almost done, because the only thing we have to do now is make our third assumption. One assumption was background metric is Minkowski. Second assumption was we're going to be very far away from the source. Third assumption is going to come now. We're going to assume that whatever happens here does not move very quickly through space. Now, how does that help us? Because what we have here is t00. And t00 is the energy density. Energy in relativity consists of a number of things. One thing is how fast things are moving through space, but also how much mass there is in that piece of space. Right? There's mc squared, if you will, the amount of mass energy, and there's the kinetic energy and maybe some other parts. The fact that we've written this now as just the energy density allows us to say, you know what, if we're going to specialize to a source where things do not move too quickly, then the amount of energy, the T00, energy density, is really just because of the mass. We're going to do away with the amount of energy that comes in because things are moving around. Now listen, I'm not saying that things are not moving around. This amount of mass that we're going to put here, the mass energy, might still depend on space itself, as in at one moment this mass is going to be here, the next one is going to be here. So it might be a mass depending on space and time. It's going to be at different positions at any moment in space and any moment in time. What I am saying is that it doesn't move very fast. So that the kinetic energy due to the motion of this mass is going to be very small and can be neglected in writing this thing here. And that then makes life very easy. Because now the only thing we have to do, if we're going to again make the assumption that things are not moving too fast, is just replace this by the amount of energy, mass moving about here in the source. And that amount of mass typically is called mu. Why not m? There's a reason, and that's if you have a binary system, multiple masses moving about, then what people typically do, not just in relativity but also in normal classical mechanics, is go to the center of mass frame. As you can mathematically approximate, not approximate it, actually equivalent, that's a better way of putting it. You can say that a bunch of masses floating about, you can equivalently write as if there's only one mass moving about, and which mass is that? It's the center of mass. The average amount of mass at any position in space. So that thing is typically called mu. So that's what we're also going to do here. We're going to assume that all these masses floating about are represented by their mutual center of mass, mu. And again, this thing might itself depend on space, and it might depend on time. Now, to be clear, this Tij had to depend on the following way in order to be a solution to the differential equation on space and time. It had to be T minus R, and apart from that, the x primed. This is me just using this thing in my center of mass coordinate here. And then there's the xi and xj, and there you have that thing over there. This is our final expression. Now there's one way of writing it. This is just notation. This whole thing, so everything away from the second derivative with respect to time, is typically called the mass moment. People who are going to do calculations, say neutron stars or just any bunch of stuff floating around where you cannot approximate everything by one single mass, are going to be well familiar with this thing. It's a first approximation to how things in total are moving. It's called the first mass moment. So here it is. That's that thing. Now, so if you want, you can also write this as this thing 2 over r, and here's your I. That's this thing. 2 derivatives given as 2 overdots here. And of course you have to put in how exactly it depends on space and time, and by the differential equation it should be like this. This is the expression that you typically find in the books. By the way, this thing is exactly the same as that thing, it's just a notational thing. And there you go. This is the expression that people use when they want to have a good approximation to how gravitational waves look given a mass distribution, some source, some mass is moving about somewhere far away in the universe, given that the gravitational wave itself moves on a non-curved space-time, and given that whatever is moving over there doesn't move close to the speed of light. And this is what you get. Now, 2 things you can do now. First of all, you can just calculate what this thing is going to look like for different sources. The one prime example, I'm not going to do this because this is going to be part of the exercises, but one thing you can do is say, well, this thing is due to two stars orbiting each other. That's a prime example of a source that emits gravitational waves. And that just simply means that you're going to, instead of saying, well, there's all these masses about, you're just going to say, you know what? There's one mass moving around some other mass, they're moving around each other. And then mu, where the center of mass of this thing is going to be very simple. It's going to be a sine or a cosine. That's simple enough. So for that particular reason, you can just say, well, this thing moves about, so that's a sine or a cosine of some frequency, in the frequency determined by the astrophysics going on here of time. And just plug this in here, do this integration, do this calculation, and just find what comes out. That's one of the exercises. That's one thing you can do. Calculate what the gravitational wave will actually look like if you put that in. One other thing you can do is, given that you know what h is, your gravitational wave perturbation, in other words, that you know exactly what the space-time curvature, your metric, is going to be at the position where you are looking, just calculate Christoffel symbols. Write down geodesic equations. See how things move because a gravitational wave has come by. And when I say when things move, I really mean gravitational wave detectors. So these two arms, how they will move due to this. This is by the standard exercise. If you know your metric tensor, you can write down the Christoffel symbols, you can write down your geodesic equations, you can solve the whole thing, and then you know how things will move in that particular space-time. In other words, how your gravitational wave detector will move. So that's another exercise. Given that you know how a binary star orbits each other, given that you've calculated what gravitational wave is, next calculate how that will make your gravitational wave detector move about. Now, before I finish, one final thing, and that has to do with this second derivative that you see here, which naturally comes out of general relativity. Note, this second derivative has nothing to do with the approximations that we've made. The being far away approximation, or the fact that we are in a Minkowski space-time approximation, has nothing to do with these approximations. The second derivative, here, came from here. And this came from the conservation of energy and momentum. So, this thing, the second derivative, is very more general than we have now derived in our particular expression. The I, so whatever is going on in here, that might be different if you make different approximations, but the fact that there's a second derivative, that is a direct consequence of the conservation of energy and momentum. Now, why is that important? Well, what we see here is that at the moment that your I, how things move about in your source here, does not have an acceleration, in other words, that if you take the second derivative with respect to time and it will give you 0, so there is no acceleration, then that means you will have no gravitational wave. That is very important. The conclusion here is you can only have gravitational waves under the condition that whatever is going on over there that produces gravitational waves has an acceleration. Now, this does have an acceleration. because you have two stars that might be moving with a constant velocity around each other, but they do not do this in the same direction at all the time. And change of direction is itself an acceleration. If you would have one star, say, and it would just move via Newton's first law in a straight line, no acceleration, then that means that the second derivative of this thing is going to be zero, no gravitational wave. And that is extremely important as a conclusion. Gravitational waves only are created when things are accelerating. And maybe you can understand this from the point of view of our starting point of general relativity, because one of the starting points of general relativity was that you can only get curvature effects at the moment that you have fictitious forces. And fictitious forces only come about when you are not staying in an inertia frame. When are you not staying in an inertia frame? At the moment that you are breaking Newton's first law, in other words, when you are accelerating. When you go to an accelerated frame, this is when you have fictitious forces. So this is when you have gravity. So this is when you have the possibility of creating gravitational waves. So there you go. Now, of course, you could say a lot more about gravitational waves, but for this video, this is quite enough. Very interesting. Don't think too much about the mathematics, because that's not the important thing. The important thing is the physics of all of this. And there we go.